evening. We are Team Fixing Refrigeration Efficiency to Sustain Health, better known as Team Fresh. Our mission is to create a vaccine refrigeration system to use in developing areas. My name is Divya, and I, along with my teammates, Jason and Kelly, will be presenting to you about the basis of our research project. We will start with a justification of our project, followed by the research problem and the research question. We will then discuss the technical background of our project with the design concept and methodology. We will end with the accomplishments as well as advice to future teams. Around the world, especially in developing nations, vaccine-preventable diseases result in high numbers of doctor's visits, hospitalizations, and deaths. There are many vaccine distribution programs implemented internationally, like the World Health Organization's extended programs on immunization. However, due to gaps and pitfalls in the vaccine distribution system, which is called the cold chain, the vaccines are not arriving to their destination in the usable condition. Improper storage leads to loss of potency over time. The World Health Organization, or WHO, recommends that vaccines be stored between 2 to 8 degrees Celsius. Vaccines are shipped to the country and go through various local levels to reach a rural area. This global distribution network of refrigeration equipment and procedures for maintaining vaccine quality during transport and storage is known as the cold chain. We will now show a video of some of the problems that arise in the cold chain. We're going to be seeing some problems that arise within the cold chain as well as the specific locations where the vaccines arrive. So here we see a control panel, and we will see the time passed, the current location of the vaccine power level, the current temperature, and the confusion level. We start the shipment from the United States. And as you can see in the airplanes, the vaccine crates are moving, causing disturbances to the vaccine. We land in a developing nation, and we use India as an example. We arrive at the airport, and here we see the vaccines sitting out in the sun as the temperature rises. The vaccines must go through customs, and 2 weeks pass by. Here at the primary vaccine store, we experience a power outage. En route to the health center, we see the vaccine carriers in the truck moving. Other delivery problems include transit failure. We also see poor road conditions en route to the health center. We arrive at the provincial vaccine store, and here we experience another power outage, and confusion level rises as we put in the ice packs, and the power level is decreasing. This is a person on a motorbike, and we see the vaccine carriers being distributed to the villages, and the confusion level is rising as well as the temperature, and the power level is decreasing rapidly. So these are some of the problems that arise in the cold chain. And we see a variety of them. We see transportation issues, electrical issues, as well as confusion. So all of these contribute to a decreased effectiveness in the vaccine. So in order to justify our project a little bit more, we have the total monetary loss of vaccines wasted due to freezing. 2 million vaccines are shipped per year, and the wastage due to freezing is approximately 14 to 35%. This results in a $140 million to $350 million loss in vaccines. We can thus define our research problem, which is improper refrigeration throughout the cold chain causes freezing of vaccines, rendering them ineffective. This then brings us to the research question of how can we design and build a cold box that better accommodates the storage requirements for temperature-sensitive vaccines. We hypothesized that by using PCM and optimizing the geometry of the cooler, we can design a cold box that prevents wastage and reduces wasted capacity in vaccine carriers. Jason will now discuss the design criteria for our product.
Thank you, David. Based on the background information that we discovered about the cold chain, we formulated a set of design criteria to guide us in the direction of a solution. The World Health Organization recommends that vaccines be stored between 2 and 8 degrees Celsius as often as possible. Therefore, our first design criteria is temperature stability. We hope to design a solution that can store vaccines consistently between 2 and 8 degrees Celsius. The second design criteria is duration of storage. Vaccine shipments can range from a few hours to up to more than a week. So we therefore decided to design for duration of storage of at least 5 days. Additionally, the solution should be easily implemented within the current cold chain. It should be cost effective. It should be simple, easily maintainable, and should maintain at least the current shipping capacity, if not increase the shipping capacity of vaccines. One of the key technologies in our goal of reaching the solution is a concept known as PCM, or phase change materials. Phase change materials function as a barrier to energy transfer between two regions. As you can see here on the right, you have a graph of ice as the temperature rises and it transforms into water. On the bottom of the graph, you have energy, and on the y-axis, you have temperature. The ice begins at -4 degrees Celsius and slowly warms up as it absorbs energy to 0 degrees Celsius. At that point, when the ice is at 0 degrees Celsius, any heat energy absorbed by the ice goes into transforming into water. So even though the ice is absorbing energy, the temperature is not changing. That's an important concept, that the temperature remains constant. In that sense, the PCM can act as an insulator. For example, if you use it in the wall of a box, it can absorb energy from outside, melt, but maintain a constant temperature inside the box. The second technology that's important is thermochromic ink sensors. Thermochromic ink sensors can detect change in temperature and also change their own color to represent that change. They usually come with 3 zones. You have a green color, which represents the ideal temperature range you want. You have 2 other zones, a red and blue. Red meaning the temperature is too high, it's too hot, and blue, the temperature is too cold. These sensors will be placed on the PCM slabs inside the box, and they can provide feedback as to what the temperature is inside the box. These 2 key technologies lead us to an overall design concept. We envision a box that employs the use of PCM, phase change materials, as a temperature stabilizer. The box on all 6 faces will be insulated to also provide more heat barriers, and the PCM slabs will be placed on the side walls and can be removable. Thermochromic ink sensors will be placed on the PCM slabs to detect freezing and to provide feedback about temperature.